Fail fast, learn fast. About a month ago, Booster 18 blew up at Massey's. Complete COPV failure. Most rocket companies? They'd shut everything down, run investigations for months, maybe release a cautious statement. SpaceX went the other direction entirely. 28 days later, that's less than 4 weeks, Booster 19 stood there fully stacked. And we're not talking about a quick patch job. This thing got the full V3 treatment. 33 Raptor 3 engines, reinforced guts, completely redesigned fuel plumbing. They didn't just fix what broke. They turned this failure into the toughest Super Heavy they've ever built. So how does a disaster turn into the fastest build and strongest design in the entire Starship program? Look, most people saw Booster 18 explode and thought, okay, setback. What they missed was the timeline. Ship 36 had a COPV blowout back in June. Then Booster 18 goes down the same way 1 month ago. Same component, same failure mode. Twice in 6 months. That's when you know it's not bad luck anymore. It's a design flaw screaming at you. Traditional aerospace? They'd form committees, write reports, schedule meetings about meetings. You might see recommendations in 6 months if you're lucky, but SpaceX doesn't operate that way. Within days, not weeks, days, their engineers had already torn into the problem and started rebuilding the entire COPV system from scratch for Booster 19. And honestly, that's what separates them. It's not about what broke. It's about how fast they learned from it. You can see the solution right there in the photos of Booster 19. Check out the lower section. 2 bright red COPVs sitting on the outside of the booster skin. That's not a tweak. That's a complete rethink. Instead of burying these pressure vessels inside where cracks hide and damage goes unnoticed, they moved everything external. Now problems show up immediately. You can literally see if something's wrong. During construction, those COPVs wear red protective armor. Sounds basic, right? But think about what's happening on that build site. Workers are welding massive steel rings, stacking sections with cranes, maneuvering heavy equipment in tight spaces. Any one of those operations could nick or scratch a COPV. Those protective covers address exactly when and where hidden damage was probably happening on earlier boosters. After installation wraps up, the covers come off and SpaceX bolts on aerodynamic fairings. Those long fin-like structures running down the booster. They call them Chinese. Now here's the smart part. Old Super Heavy versions mounted COPVs side by side in pairs, which meant short, chunky Chinese that created a ton of drag on the way up. Version 3 lines them up single file instead. Longer, sleeker fairings that actually cut drag during ascent. So the safety fix improved aerodynamics at the same time. That's the kind of multi-benefit thinking that gets me excited about this program. And they didn't stop at redesigning mounting. Behind Massey's, there's now a dedicated test facility with 4 bays just for COPVs. Every single pressure vessel gets put through verification testing before it gets anywhere near a flight vehicle. Between Ship 36 failing and Booster 19 standing ready, the entire production chain changed. How they manufacture these things, how they test them, how they install them, how they protect them. Does that sound like a company just slapping band-aids on problems? Or building systems that actually learn from stress? The timing here matters more than it might seem at first. Right as Booster 19 hit full stack, NASA's new boss, Jared Isaacman, dropped this bombshell on X. We are going to build a moon base. Not study one, not evaluate feasibility. Build one. Elon's reply was just, awesome. One word. But if you understand what's required to actually construct a permanent lunar outpost, that word carries serious weight. A real moon base isn't one mission or even 10 missions. You're talking hundreds of tons of equipment hauled to the lunar surface, living modules, power generation, life support, rovers, manufacturing gear, equipment to process local resources into usable materials. Every single HLS mission needs somewhere between 8 and 14 tanker flights to refuel in low Earth orbit before it can carry meaningful cargo to the moon. Do the math. You're looking at potentially hundreds of Starship launches compressed into just a few years to get initial infrastructure standing. Right now, Starship turnaround time measures in months per vehicle. At that pace, building a functioning moon base would stretch out over decades. The timeline just doesn't work. Suddenly, version 3 isn't some experimental upgrade anymore. It's the critical hardware that has to prove it can handle the most brutal operational tempo any launch system has ever faced. Which brings us to why SpaceX made Super Heavy so much more powerful. Booster 19 packs 33 Raptor 3 engines. Each one cranks out roughly 280 tons of thrust, compared to Raptor 2's 230 tons. Add it all up and you're looking at 9,200 tons total. That's about 1,600 tons more than version 2 delivered. To put that in perspective, they basically added 3 Saturn V first stages worth of extra power to a vehicle that was already twice as powerful as Saturn V. The physics work in your favor here. More thrust means you're burning propellant faster, which translates to shorter burn time for the same fuel load. The rocket accelerates harder, climbs out of Earth's gravity well quicker. That cuts gravity losses by something like 20 to 30%. By the time the booster separates, the upper stage is already moving faster and higher, so it needs less of its own fuel to make orbit. End result? More cargo delivered using the exact same amount of propellant. For lunar missions where every kilogram of payload counts, that's huge. But, and this is important, more thrust creates problems of its own. All that extra power generates stronger resonant forces rippling through the structure. Super Heavy stands 70 meters tall with thin stainless steel walls because they're optimizing for low mass. That makes it vulnerable to something called Pogo oscillation. Basically, pressure waves in the fuel lines start interacting with the rocket's natural vibration frequencies. If that feedback loop gets going, it can shake the vehicle apart from the inside. SpaceX's answer was to fundamentally beef up the internal skeleton. The methane tank now has 96 internal stringers, compared to 76 in earlier versions. That's a 26% jump in structural reinforcement. And these aren't just random additions. They're strategically positioned to increase stiffness and dampen out vibrations that would have destroyed previous generations. The power boost and the structural upgrade happen together, not one after the other. Building systems that get stronger as the demands on them increase. Of course, structural strength doesn't mean much if you can't reliably feed all 33 of those Raptor 3 engines. Which brings us to probably the most impressive upgrade on version 3. One nobody saw until Booster 18's shell ruptured and gave us a view of the internals. Running straight down the center of the booster is this absolutely massive fuel downcomer. Best estimates put it around 3 meters in diameter. Think about that for a second. That's nearly as wide as an entire Falcon 9 booster. They essentially built a Falcon 9-sized pipe inside Super Heavy. Why go that extreme? Because it solves multiple problems at once. First, it handles the dramatically higher propellant flow rate that Raptor 3 demands. Second, the larger diameter and smoother flow characteristics actually reduce pressure oscillations, which helps fight that Pogo problem we just talked about. Third, this downcomer can store reserve propellant for the boost-back burn and landing, which means they don't need a separate complicated header tank system. Total propellant capacity hits around 3,650 tons. There's also an operational advantage that becomes critical when you're trying to reuse these things quickly. A bigger downcomer enables faster, more stable propellant flow during the boost-back flip right after stage separation. When you're trying to land a 70-meter rocket back at the launch tower using giant chopstick arms, stability during that flip is basically the difference between success and a very expensive crash. On the outside, you can spot the liquid oxygen autogenous pressurization pipes running around the aft section. Instead of carrying separate tanks of pressurization gas, this system uses gaseous oxygen, generated by the Raptor engines themselves, and routes it back into the main LOX tank to keep pressure stable throughout the flight. Fewer parts, less weight, higher reliability. Every component serves multiple functions. The whole system has redundancies baked in. That's not just an upgrade, it's a resilience philosophy. What really caught people off guard was the construction timeline. Booster 18 took 175 days from initial ring stacking to full integration. That's basically 6 months. Booster 19, with every single version 3 upgrade we've been talking about, hit full stack in 28 days. They didn't slow down to add safety features. They sped up while implementing the most comprehensive upgrade package in Starship's entire development history. That 28-day record isn't just about building fast. It proves these designs actually work at production scale. You can't build a moon base with vehicles that take half a year to assemble. You need manufacturing systems that can deliver flight-ready hardware in weeks. SpaceX's vertical integration is what makes this possible. They design it, test it, build it, and put it together all in-house at Starbase. Feedback loops that would take months at traditional aerospace companies happen in days or even hours here. When Booster 18 failed, that physical proximity let them iterate immediately. The lessons didn't wait for formal investigation reports. They fed directly into Booster 19's construction while it was actively happening. There's something deeper going on here than just speed. Truly resilient systems don't just resist failure, they use stress and setbacks to evolve into something stronger. Booster 18 exploding didn't slow down the program. It accelerated improvements that might have taken years to discover through careful, conservative testing. Now the challenge shifts. It's not about proving individual upgrades work anymore. It's about demonstrating the sustained operational tempo that actually building a moon base demands. So what did Booster 18's failure really teach us? It wasn't a setback. It was proof the philosophy works. Fail fast, learn fast, build stronger. 28 days from catastrophic explosion to the most advanced Super Heavy they've ever stacked. External COPVs, 33 Raptor 3 engines, reinforced structure, completely redesigned fuel systems. They didn't repair it. They transformed it. That's what anti-fragile engineering looks like. And it's exactly what Isaac Mann's moon base vision needs, because building a permanent lunar outpost doesn't require perfect rockets. It requires resilient ones that can launch again and again without breaking down. Version 3 is that rocket. If this breakdown added value for you, hit that like button and subscribe to New Space Review. We'll keep diving deep into SpaceX's breakthroughs as they happen. Drop Go SpaceX in the comments if you're excited to watch V3 fly. And speaking of lunar operations, click that video on your screen right now. Elon just revealed Starship's solution for mining resources on the moon, and honestly, the method is mind-blowing. Thanks for watching. I'll see you in the next one.